This is a talk about the impact of robotics and artificial intelligence on oceanographic sampling, but it's also a case in point to talk about the broader issues related to what's needed for understanding oceans and ocean processes today. So this is going to be at a 10,000 foot level in given the amount of time we have. And I want to start off by acknowledging the host of different entities who supported my work over the last 10 to 15 years and sort of stress on the notion of what undersampling is about. And Walter Monk, one of the preeminent oceanographers on the planet, who passed away recently, unfortunately, had this very interesting and simple notion that most of the previous century could be called a century of undersampling, which basically gets down to the point of, well, we really don't understand what's going on in the ocean. So, with my background coming from technology in computer science, um, I have been focusing on the need for advanced methods in computation, which would allow machines to be smart enough and sustainable enough to cover wide areas spatially and over a span of time. So essentially being in situ to be able to do intelligent robotic sampling in ways that are sustainable. So that's really my research vision going forward. So it's to build these tools, then they need to be cost effective so that we can understand how the world is changing. And very simply put, in terms of the motivation, the notion here is to bring a collective of robots that can measure a chunk of the ocean and be coordinated in some way across the space and time, and making measurements which are important to physical and biological oceanography using methods in automation and control and spatial statistics and artificial intelligence. So the idea here is to be able to build these tools which are low cost and sustainable, and to have them open source so that you can essentially have a community of folks who can actually work on it and pull this forward. And scalability is important. So it's not just about trying to get one particular vehicle, but a range of vehicles to be able to work together as a cohort in the ocean. And so where this has led me to is essentially bring in a range of techniques which I'll sort of briefly touch on in this talk, which relate to computation and decision making, human level decision making in situ on machines which are in the ocean, and essentially giving us an extension of the human senses to do data analysis, visualization, and making machines smarter. A lot of this work has been as a consequence of my efforts, having spent 10 years at NASA uh, and being involved in two deep space missions. One on board the NASA Deep Space One experimental mission in 1999, and the command and control of the two rovers on the surface of Mars, um, which has garnered quite a lot of attention. Scientifically, the notion is to enable robots to be able to adapt dynamically to events at scale. And to do so, you require certain methods that you need to bring in from engineering, including a very structured, formalized way in which you deal with time and resources in the computational code itself. And to be able to do this, to not just do ones and twos, but to be able to do this for a long term, to keep the engineering, which is really to sustain engineering, which is really the most expensive part of how things work when it comes to building anything which has to work out in the real world. So that's sort of that's the core of where I'm coming from. And my own personal intention is to impact by having these tools available for everyone to solve real world problems where human cognition can be brought to bear, but in machines, so that machines can go off and do the things that we expect human beings to do. And to demonstrate this in the harsh environment that we know is the ocean. And one aspect of that is, of course, the core notion of automated planning, which I will briefly touch on. It is to take the concepts that exist and to make them work, and not to sort of engage sustained algorithmic efforts in building that out. So from a thematic perspective, I have my research has been in a number of different areas that you can see on the left. And the practice of how I've sort of pulled all of this together over the last 15 to 20 years has been engaging in space science, ocean science, but using tools from artificial intelligence and robotics to enable real world experimentation. And to do this in ways that the real world experimentation informs academic research, which can go back to be fielded in the real world, which in turn goes back again. So there's sort of a virtuous cycle where you can inform the academic work by what goes on and what fails in the real world, and vice versa. So the talk itself is going to be very broad, as I mentioned. I'll start with the themes, motivations, talk a little bit about robotics and at sea and how many of us envision it. Talk about sampling and the applications that it engenders and where I think we are headed. So it's a very broad-based talk to sort of give you a perspective of where things are. But first, a very interesting and a simple question to ask is, why do we explore? And the why do we explore has a range of different answers to it depending on who you ask. But I found this particular quote from a noted historian in the 19th century in the US as to really sort of say there is something out there that we want to explore, we want to understand, and to understand and obtain the knowledge for figuring out how things work in this world. So why do we explore is really at the start of where things for me have certainly gone, and to build on capacities that are beyond the simple notion of this picture that you're seeing here with doing sampling in particular, and but to sort of engage in ways where we can go from the macro to the micro and understand, for example, how a hypothetical molecule from the atmosphere, a carbon dioxide molecule, moves through the atmosphere, through the air-sea interface into the ocean and how it evolves. If we can ever get to that point of understanding, I think we've achieved a phenomenal amount of knowledge that we could exploit in making the world much better. So we can use that as a way to understand processes. Your picture on the right shows you upwelling phenomena where chunks of water get pushed up into the surface, carrying a load of nutrients which can trigger a bloom. So what you're seeing is a picture of a bloom at the top of the bay, which happens to be the Monterey Bay, where I worked for about close to a decade, and use the physical, biological aspects to understand why the bloom occurs and when it occurs under what conditions. And here is an example from 2004 satellite imagery of that same location, Monterey Bay in California, which is to sort of highlight the extent and spread of the bloom to understand its dynamics. What's causing it? Where is it going? Why is it developing? Why is it collapsing? And as a notion to understand water column processes. And anthropogenic impact in these connections in these environments always have some significant connections. And here is an example where a river in the bay actually provides a huge nutrient load to the Monterey Bay, changing the dynamics of these biogeophysical processes that this is showing. So I'm going to switch gears multiple times, and I'm going to start by switching gears first here by saying, why do we need robots in any domain? And fundamentally, it boils down to safety, cost, and how methods of operation. And the methods of operation is probably the most interesting because that allows us to scale, to think about making observations in ways that we've never thought about, because machines are enabling the same capacity to return observations or make measurements that human beings were doing. Machines can do a lot more in certain circumstances than what human beings can do, and certainly in the ocean and certainly on Mars, machines can do a far better job that we know. Cost is significant. We, over time, as we build the capacity for machine intelligence and robots, they don't really need life support, so they can operate all hours of the day and under all conditions. And because they can operate under all conditions, especially at sea, safety becomes a paramount issue when you're using, when you want to think about the notion of why robots are used. So, what is a robot, and what does it mean to be using robotics? The typical Hollywood notion of a robot is what you're seeing on the screen, but to a large extent, robots are not as functional as Hollywood would like you to believe, but they're functional in other ways which are useful, like the ones on the surface of Mars, for instance, aerial vehicles that are now all over in the news these days, that are visible, and satellites and spacecraft, which are also robots in a certain way. Most of all, what's relevant here is the underwater vehicles, gliders, autonomous underwater vehicles, AUVs, which are powered, and those that are relevant for taking measurements in the ocean, which is really the subject of what we're talking about. But there are other kinds of robots, like what you're seeing here. And these robots are all doing different things altogether.
Astrobiology is the
And
study of life
essentially,
in the universe and covers everything.
we are trying to get our grips around what are the things that robots can do, including being a collection of measuring devices which are static, not moving, immobile robots, which are collecting information over time and relaying that at different scales. From small little lakes to vaster regions, these robots can and have been used. And they all sort of use the basic notion of being able to sense or perceive the environment and collect the data that we had traditionally been using human beings to collect. So the notion of a robot is not all that different in the sense that it is able to perceive the environment and transmit that data for human consumption. And fundamentally, it could be a range of different devices in space, aerial, surface, underwater, on trees, you name it. But what are robots useful for? And where they have become useful lately is in disaster relief, or at least understanding the scales of disasters that we need to be dealing with and what to do with. And monitoring and looking at ways in which we can monitor our environment and to look for issues of concerns when it comes to security and other forces. So here is these are all robots and videos about observing and taking measurements at home at outside, but there are also those that are relevant for inside and in domestic environments, much like very similar to those that are collecting data anywhere, including on the surface of Mars. At the bottom, what you're seeing is um, the 2003 Mars rover mission collecting data and samples based on software that I and my team had developed to do the command and control of these rovers. Where and when to sample in this case was decided by human beings, but you can imagine that if you can replace that cognitive burden and put it inside the machine, you would get a similar result. So these are these are kinds of vehicles that we've been looking at and working with. But here is an autonomous underwater vehicle, which is essentially effectively a computer with a propeller that you can throw in and has a range of instrumentation to make measurements and for navigation, for control, for science, and to be able to move without any tether where the computation is happening on board to tell it what to do next. And you can see that the typical launch is very straightforward and simple. In fact, this is one of the most robust AUVs on the planet and is designed and built at a lab that I'm affiliated with in Portugal. And similarly, there are these vehicles which are aerial vehicles, which are really incredibly inexpensive, low cost. And when you attach sensors to them, they can bring that data back to you very rapidly, which you can use for doing any form of analysis. So all of this is about platforms, hardware, which you can use to extend the human senses and extend the reach of the human senses. So let's talk about what goes inside those platforms. And we start with the notion of understanding what inference is. And fundamentally, inference is about making decisions and inferring what to do next. So this is something human beings do naturally. But the question then is, why do you want this kind of a capability on a robot? Well, you need it because you are dealing with an uncertain environment where you have a very poor model or understanding of what that environment is and how it's behaving. Number one. Number two is you want to be able to observe this environment. In our case, the upper ocean. You want to observe it at large scales of space and time. But in the process of using these robots, you also want to be able to deploy them and let them make decisions so that those decisions are now removed from a human, the operator, and reduces her or his cognitive burden to be able to do things that a human would have normally done. So essentially, you're sort of outsourcing the nature of observations and how you want to collect them, collect data, and to be able to do it in a way that is continuous, and automatic, and to be able to sort of relieve this burden while also taking advantage of any kind of opportunism in finding things that had not been seen before. But this comes at some cost because fundamentally making these measurements or sampling, as we call it, is requires a notion of dealing with finite time, energy, because your robot will have finite energy on board, and therefore there's a certain amount of time that you have to be able to sample. And these resources are finite and you're dealing with an environment which is uncertain. So this dichotomy of, dealing with time and energy in this environment makes things to be very difficult. So what you're really interested in dealing with this dichotomy is balancing future goals with what you expect a robot to do with current opportunities. That is something that's of interest that you can make measurements with and while keeping in track the longer term needs. This is again something that human beings do extremely well. So we're going to talk a little bit about how these things work in the ocean. We're going to have AUVs. How do they get deployed? How do they get recovered? In general, the strategy has been that for autonomous underwater vehicles, you deploy from a ship, drop them in the rough area where you want them to operate. And in the past, the ships used to be on the surface tracking these vehicles through some form of acoustic communication and making sure that they haven't been lost or haven't gotten stuck or hit something down at the bottom if there is shallow water. And that has actually given way to what is in the second tier, where the ship is free to be able to do other things and move out of the area and let the AUV in the water column do what it needs to be doing. And to a large extent, this has happened because of the advancement of these techniques to be able to infer and to do deliberation on board. Where all of this is going ultimately through multiple steps, the end goal is to be able to deploy a bunch of AUVs in the water column. And they can sustain themselves in various ways, including with being able to dock autonomously, that is, automatically to a station which has power to be able to charge the batteries on the AEV when it's depleted and to downlink the data from the AEV from what it's collected. And so essentially they are roaming vehicles just like fish, but this is a long-term idea and a concept that we are not anywhere near from. So all of this is sort of to give you a big picture view of where things are. And I want to sort of switch gears to where I've personally come from to have made some form of an impact to the kinds of decision making that we're talking about. So this is a very quick introduction to my own research trajectory in autonomous systems, starting with flying what was called the remote agent experiment, the first artificial intelligence system in space. We took control of a spacecraft 65 million miles from Earth, and the idea was to demonstrate the technology by controlling the spacecraft towards a particular asteroid and then take images and to move on. This was an experiment in 1 week in 1999, which we did really well, and that uh, defined the notion of what can and should be done in space, certainly in terms of autonomous systems. And then fast forward to 2003, when we were asked to do the command and control for the Mars exploration rovers. And that was a significant effort. And from there, essentially, I was invited to join the Monterey Bay Aquarium Research Institute, which is a flip from or sudden change from space to down to the marine environment. And that's really where I've been for the last close to 15 plus years, actually close to 20 years, and executed on a number of projects. This one is about bringing the human into the loop for autonomous systems, funded by the National Science Foundation, and then taking this concept in ways that bring a new notion of how to observe a chunk of the ocean using multiple vehicles from space, aerial, surface, underwater, and providing decision support. All of this, it's important that cost is an issue and be factored in. It isn't just a matter of where you are or which part of the world you are, but cost is a significant factor that the robotics community has had to grapple with. Just going to sea is hard enough, getting ship time, but once you're at sea deploying and recovering vehicles, as you're seeing here in these pictures, is actually not that trivial. So the notion that you can have a university perform these kinds of experiments at sea, collect data, do the analysis for science, not so much as developing the technology. That is really good, and that's where things are heading, this mix of engineering and science. But the cost has to be factored in to operate sustainably over long periods of time. And so this is where actually robotics and computational methods have actually made fairly serious inroads. Scale matters, and we are looking at phenomena which are very large. So a single robot is not typically going to help you. Multiple robots, how to control them, what kinds of software goes inside, how to process the data. These are the key issues that are important to enable how we can do science at scale with the instrumentation, the techniques that we have. Switching gears, in terms of enabling such science to be able to make decisions on board, we need inference, which is to have decision making, having machines think the way human beings do on board. So, what is inference, first of all? And by definition, it's to arrive at a certain conclusion, a logical conclusion, given the available facts. And you have to know what's the context in which these facts are available and when they're available and how they're available. So all the state assumptions have to be wrapped in. So a very simple inference chain, for instance, is A implies B and B implies C. Therefore, the inference is A implies C. And A, B, and C could be anything from, seeing clouds in the sky to inferring that rain is going to happen. So these kinds of inference chains are critical to how decisions are made on board. This is how human beings also think. Perhaps not so stylistically, but along the lines of what you're seeing here on the screen. And a lot of it has to do with these making these complex choices, which you can factor in if they are nice and clean and that you can partition into trees of some sort. And you're essentially making choices between which branch of the tree to actually go down off. So inferencing and decision making at the heart of these kinds of deliberative techniques that we really call as planning, that is at the heart of what we're trying to accomplish in the ocean sciences using methods in robotics and AI. And here's a really good textbook, and it's the standard textbook that three friends of mine have written up some time ago, and there's a newer edition, but this is a book that is really influential and talks about what the field is doing, and the field is called automated planning. So what is planning? Planning is a notion of being able to synthesize the sets of actions you need to take. And the you can be a human being or a robot, whatever. It's a set of actions that you need to take and formulate to be able to achieve a goal in the future or in the near future. So that is sort of the cognitive way of thinking of all human beings is we plan all the time, and we plan and some of these plans don't work or these plans are useless, and that is fine. But the act of planning, the act of anticipating, the act of understanding what are the possible ways in which you can accomplish a goal is fundamental to how we human beings think. And so acting without planning is very reflexive, or you are reactive. But acting with a plan is deliberative, where there's some purpose to it, and the purpose can change, and the plans will definitely change. But the process of making this choice and the organization of these actions in space and time is critical. And this is exemplified by what Dwight Eisenhower, the Supreme Commander of the Allied forces in the Second World War, and a future president of the United States at that time, really said, encapsulating in planning for battle. I've always found that plans are useless, but planning is indispensable. Failing to plan is planning to fail. And really, it encapsulates the fundamental notion behind the architecture that the software architecture that my colleagues and I have designed, implemented, and fielded on AUVs on a range of different vehicles, including aerial, surface, underwater vehicles for the ocean to sample, to make measurements. And the notion here is that if you think about an ROV, the picture on the right has a remotely operated vehicle, which are tethered vehicles to a ship. The way you think of these vehicles are that there are really four actors: the vehicle itself, the pilot who's guiding the vehicle, an arm operator, since most ROVs, especially the large ones, have an arm to be able to touch, feel, manipulate in the ocean. Um, and then there's a scientist. So these are the four principal actors when you're looking at an ROV. And this is an example. You can exemplify this notion of these actors in various different scenarios, whether they're flying a plane or driving a tank or a truck or whatever. So the notion here is that they're actually split along multiple axes. One is the functional scope as to what they're doing. Each of those actors is doing very different things. The vehicle, the robot, is essentially receiving commands and making observations. The commands are sent down to the robot, and observations are flowed up through the robot to the the person who's handling the payload, the arm, for instance, or the pilot who's navigating the vehicle. And that information in turn is filtered up to the scientist to say whether something has been accomplished or not, whether they've been able to pick up a rock at the bottom of the ocean, or have been able to grab a crab which is running along in the benthic plane, or manipulating any kind of an object. So essentially, this structure of the functional scope and the temporal scope, it has to deal with how quickly you respond or you deal with the issues that you have to deal with. So at the bottom, the robot has to be incredibly fast, but at an abstracted level, the scientist can sit and abstract what's going on and to think through what the robot should be doing now, 10 minutes ahead, maybe even a couple of hours ahead. So essentially, there is this dichotomy between the functional and the temporal scope, but they play together to make this cohort of actors working together to accomplish a certain goal. And that is at the basis of this piece of software called T-Rex, the Teleo Reactive Executive. It's pretty much the only deliberative system that uses cognitive capabilities, which has been applied routinely and consistently in ocean science for the last 10 years. And this is freely available, open source. I believe that is the right address, but the learning curve is fairly high because it revolves around building an operational model of the robot what it can do, when it can do it, and how it should do it. And that model is not easy to build. But once it's built, essentially you're reusing that model over and over again for a range of different applications. So this is starting from my early slides. This is a way to demonstrate that a core capacity can be reused and scaled up to do lots of different things while the engineering is sustainable while keeping in sync with uh, as your ambitions and your tasks and your missions grow. And that is the purpose of T-Rex. So deliberation and execution are intertwined. Deliberation, if you recall, is the ability to think through and have inference, make choices. Reaction and execution are simply to act on and to be able to do that very quickly. So what you're seeing in this architecture is both the the tension between the functional and the temporal scopes. The functional scopes are across a range of these actors. In this case, you have five of the blue actors, and there's the sixth one, which is an interface to an Iridium satellite communication, which is a bit of a dummy. Essentially, it receives in commands from shore. And the idea here is that a scientist can sit on shore and give high-level commands to tell the vehicle what he or she needs to do from the comfort of his or her office, and the vehicle goes off and do it as an extension of the human senses. So once the model has been built, the system knows how it needs to use it, then the key issue is what it encounters and how it deals with the environment without communicating or having the ability to communicate back to shore. All of that decision making happens on board. So there have been a range of different applications. I'm going to sort of speed through to give you a perspective of what those are. Here's one which has two AUVs, and these are all propeller-driven vehicles with CPU, compute power. In this case, what you're seeing is a front tracking. One vehicle which has more sensors, the smaller of the two, is able to track where the front is, relays that information back over satellite communication to the other vehicle, which is nearby, but since they can't communicate directly, it goes to the satellite, comes down, and goes back into the vehicle. The other vehicle, which is much larger, has samplers, water samplers, which can take samples at the front. And bring those samples back to shore for analysis by human beings in the lab. A similar notion is with what's called a wire walker, which is a green energy vertical profiler which goes up and down in the water column with CTD, the conductivity, temperature, density instrument that is very common in ocean science. And essentially here the experiment was more engineering to understand the dynamics of two very different vehicles, when they can sample and how the samples are correlated or not, which is to say, how close should you be um, for two vehicles to sample for it to make sense. In this case, the wire walker, the picture on the right, the image that you see, is essentially a vertical piece of equipment with the CDD inside, and it's floating. It's powered by the waves, so it's floating in the water column. And the AUV that you see is in the water column that's just gone into the water now, is essentially chasing this. And we don't know where the wire walker is going to go because the current structure is not very clear and we don't really know. And it can take the wire walker as a Lagrangian piece of equipment, it can take it anywhere. And the vehicle essentially is following it. And ever so often they are making measurements, and then we get all those measurements back to shore and we try to see what makes sense. How close should these measurements should be or should not. Similar, a somewhat Similar experiment where we were tracking what are called subsurface chlorophyll max, which is the mass of chlorophyll which feeds a bloom. A bloom is a biological event, a biogeophysical event at the surface where there is uptake of nutrients by small organisms, phytoplankton, the zooplankton, essentially, and there's an explosion of growth when that can lead to depletion in oxygen in the upper water column. But here, what we were trying to investigate is can we track a bloom in space and time? And again, we have two AUVs. We were driven by a remote sensing image um, that you see on the left-hand side showing the red tinge of the bloom. And we were trying to see where that bloom is being fed because it requires a nutrient mass from the subsurface chlorophyll mass feeding it. And so what you saw in the animation on the right-hand side was essentially this tracking, this dance, this choreography, completely hands-free, no human being is involved, the two robots in the water column. And what you're seeing there is actually the Monterey Canyon, which is one of the deepest in the United States in California. So these are experiments, and here's another one which is mostly offshore, but with a uh, what with a genetic sampler called the ESP, Environmental Sampling Processor, with two ships. The ESP hung on a float, as this image shows here, and again the AUV actually tracking it in space and time. So this is a vignette of a series of experiments that were done in off Portugal 2013. My collaborator and I were the principals. Using a Navy ship, we were able to demonstrate the coordination between multiple assets, similar to an experiment we did in 2013, 2014 of chasing tagged mola mola in space and time. And you're seeing an animation of an aerial vehicle spotting a mola mola visually, relaying that position, and then getting AUVs and a surface vehicle, an ASV, autonomous surface vehicle, to sort of come near these fish and track them as they're moving. The sunfish bask in the sun because they're cold-blooded, and so the biologists that we were working with tagged them, and we were able to track them in over space and time. And further experiments in measuring and understanding the three-dimensional structure of a subsurface chlorophyll max. This is understanding not just how to track the subsurface chlorophyll max, but how does it, what's the shape of um, this blob underwater. This is what we did in Norway with my PhD student there, and the results were in the Science Robotics. And finally, here in the open ocean in 2018, using the Schmidt Ocean Institute research vessel, we were able to track and analyze fronts which hadn't been looked at for close to 20, 25 years in the open ocean, about 1,000 kilometers from San Diego. And essentially here, the ship was just a sort of a head of an octopus, and we had deployed 10 AUVs and aerial vehicles to sort of detect where the front was and then figure out the structure of the front as it varied over time. So these are all methods, computational methods that have a particular trait in that they involve decision making, decision theoretic. Um, but where is all of this heading? And my estimation is that we are simply moving in a direction where an amalgamation of techniques, not just in AI, not just in ML or robotics, but an amalgamation of techniques across these disciplines, including what are called graphical models, Bayesian inference models, spatial statistics is going to be critical to be able to understand how things work. And central to how understanding how things work is the ability of a machine to actually learn online, ideally, and to have that online learning process be part of the sense plan act cycle that we've seen in the past. Now, in this case, it'll become sense, plan, learn, and act. So essentially, you're constantly observing the environment, the physical environment, and you're learning how you make those measurements, how things change in real time, and as a consequence, having your models change while you're working in software on board. So this is a far stretch. We are nowhere near, but this is the idea, and this is the intent and desire to get to that place. And one vision to make that happen is through coordinated observations, going from very fine scale to the mesoscale. The mesoscale is about 50 square kilometers, a patch of the ocean that oceanographers think is representative of the ocean and its environment. So the notion here is we would want to be able to observe across different scales of synopticity. That is, to be able to take an image and to be able to understand at through that image what processes are going on, but to do it at different levels so that you have subsynoptic to hypersynoptic all the way. Subsynoptic at the lowest at the power point of this inverse pyramid with an AUV underwater, NASV, which is even slower, sitting on the surface, a more synoptic, hypersynoptic, perhaps, aerial vehicle, which is flying much faster, even if it can't stay in the air for too long. And of course, satellites, and these are in particular small satellites that universities can and have been building and launching on their own, carrying pretty much either a single or maybe one or maybe two payloads at most, scientific payloads, to observe the ocean. So all of this is doable. It hasn't been put together, but it's not the hardware that is at the center of this vision. It's really the software, which is where ocean models and modeling actually become critical to making a concept like this mobile portable ocean robotic observatory, making this viable. So it would be an assimilation of data from multiple assets at sea, in space, aerial, surface, and underwater, mobile, immobile, onshore, offshore, and to use that as data sources to assimilate into a model, which may be not very skilled, but as it observes and obtains and assimilates this data, the skill level continuously increases. And it increases in part because the projections, the predictions that it makes can be tested by looking for areas or domains in the ocean where the uncertainty or outcome or entropy is extremely high, and to use that entropy measure to drive where the robots, especially the mobile robots, should go. So essentially, the less you understand, the more you want to deploy those robots to those specific locations targeted by the model. So the model becomes essentially the brain of what we want to encapsulate, and it increases its own understanding and predictive capacity as it assimilates more and more data. So this is sort of a cycle over time that can ensure that the kinds of predictions that the model generates becomes better and better. And we believe we should be heading in that direction, starting with the notion that you can have an AUV which has been completely programmed to observe at the fine scale, including what kinds of particles, microparticles exist in the water column, and to be able to identify them in situ as it's moving, and to be able to categorize and show that there's a collection of these particles, whatever they are, in specific regions and hotspots, and to be able to sample those hotspots in real time. All of this with the scientists sitting on shore, and directing the vehicle through simple commands. So this is where I believe that ocean science is heading. And it's not just robotics, it's not just AI, but it's a collection and it'll be a cohort of people and from different disciplines, starting from ecology, genetics, chemistry, and certainly marine sciences, but also working with people in mathematics, computer science, and engineering and maritime law to tell us how we can stitch these kinds of um, information theoretic approaches to sampling. And all of this is happening because really we are at a cusp with increasing reliance on machines, with robots out at sea, getting data at much, much larger volumes. Still not enough, but still they're much more larger volumes than what we've had in the past. And this requires and needs to have a notion of how these vehicles can sustain themselves in the light of failures, in the light of events that had not been programmed for, and have these autonomous systems be robust to be able to deal with these changes that are often unpredictable. And given that there is some work going on in this area, there's a fair amount of interest, not just in the ocean science, but elsewhere. These open questions, open research questions are being dealt with as we go ahead. And this is actually a great time to be in ocean science and engineering because these portals are opening up and there would be a range of different opportunities for people who are interested in looking at how methods in AI, robotics, and automation can actually have an impact. There are a few representative publications of mine, some in science. I'm happy to talk to anyone. I will be in Ghana and happy to interact. My website and email is available right from the front of this presentation. But you can certainly feel free to reach out and happy to answer any questions and comments, queries. Thank you.